Welcome everyone to today's Robust Optimization webinar. It's my great pleasure to introduce today's speaker, Olga Kuryatnikova. Olga got her PhD from Tilburg University in the Operation Research and Econometrics group. Then she joined the Western University in Canada for a postdoc. And now she's at Erasmus University in Rotterdam as an assistant professor. And today she's going to enlighten us about two-stage robust quadratic optimization with equalities. So without further ado, the mic and the screen is yours, Olga.
Thanks a lot, Ahmad Reza. And thanks, Ahmad Reza and Yanis, for letting me talk here. I'm very glad to be here today. And indeed, so I'll talk about two-stage robust optimization, and I will show its application to optimal power flow, because this structure is very typical for optimal power flow. And this is my postdoc project. So we did it a couple of years ago with Bisan Gadar, who was my postdoc supervisor, and Daniel Molzan. And I am not a robust optimization person, so I'm sorry in advance for any like strange words or whatever I say maybe imprecisely. And I would be very glad for any feedback or ideas or corrections, because maybe there could be definitely a better way to do it than what we did. So let's start. And that's how I start. So we will talk about ACOPF, alternating current optimal power flow. And I think some of them have heard of this problem, maybe some not, so I will just still introduce it. The idea is that we will have a power network. A power network will consist of power buses, and a bus can be either something that generates power or something that consumes power. So it can be either a power station, or it can be a house or a building which consumes power. It can be some substation, transformer, etc. And then all buses are connected by lines. And a line is literally the transmission or distribution line, which we see outside these wires. These are the lines, and they connect our buses. So that's the system. And in the system, our problem will consist of the following. We will want to decide the values of power and voltage, which we set up in generators, such that the cost of generation is minimized, and such that we have several constraints. First, we should stay within physical limits of our generators and our lines, and the limits will be imposed on voltage, current, and power. And second, we will need to satisfy the demands. And this actually second part is the main source of uncertainty in this particular talk. So we will talk about, ACOPF. ACOPF will be under uncertainty. Uncertainty can come either from demand, because we know sort of a pattern of demand pretty well, that we consume much in the morning, in the evening, we consume less during the day usually, but we don't know the exact values. We can predict them pretty well, but not perfectly well. And the same with the renewables. So we also have renewables added to our consumption. Here is a picture of solar renewables. And we also sort of know the pattern, but we don't know the exact values. And that creates the uncertainty. And the idea here is that this problem is solved every 15 minutes in practice. So we actually can predict within the 50 minutes, not too badly, but still not perfectly. So the uncertainty, which I'm going to talk about, is not a super big events uncertainty. It's more like noise-like uncertainty, this error in 15 minutes prediction. So that's the idea of the problem. Maybe any questions at this point? Okay, then let's formalize it. If we formalize it, we will get the following. We will have cost minimization, and cost minimization for us will be a convex quadratic function, so it's easy. And we will have two types of variables here, y and x. In the cost, you see only y. Y is our control variable. So this is the variable which we set up in the generator as an operator. And that's the variable which we really need to know, because that's our main indicator, something that we're really going to use. And also for our control variables, usually these are, like powers on a certain buses, some types of voltages on the functions of voltages on a certain buses, voltage magnitudes. These things the operators can set. And we also know limits on these things. So we want that they are set up within certain limits. This is also easy. And then the hard part comes. So the hard part comes from the fact that power and voltage, they are all nonlinearly related to each other. So basically what happens is that the operator sets up certain parameters, and then the system comes to equilibrium. And this equilibrium is described by this system of equations. This is a quadratic system of equations in our variable x, and x is a so-called state variable. So this is the variable which we do not control. It is just decided by the system after uncertainty realization. And in our case, x will be voltages in rectangular coordinates for those who knows the problem. So this is a system of non-convex quadratic equations, but it's a square system. So as many variables as equations. Yes, as I see, there is a question by Dick.
Yeah, so what are typical dimensions of the variables?
Typical dimensions are, like in a real system, it would be something started from 6,000 buses, and x is twice this number, so it will be like 12,000. We also work with smaller systems, but realistic would be something like that, 6 to 15,000.
Okay, yeah, thanks.
And y is a bit less, but yeah. Okay, maybe other questions? So this was the hard part, and another hard part for us here is another set of non-convex things, but those are inequalities. They're also they're related to other indicators in the system, and they also come basically from the physical laws, how the current flows on the lines, and basically they're motivated by energy losses. So in fact, what people do in practice, they kind of ignore this. They linearize this using certain assumptions, and they solve it like that. And up to now, it worked pretty well. And the main problem why it doesn't work well anymore is the uncertainty, and in particular, the uncertainty in renewables. So because there is uncertainty in renewables, these nonlinearities become more important, and it gets more interesting actually to really look at the nonlinear things, not at the current type of linearization. So now this is the problem, and this problem will have a two-stage nature, in the sense that as long as I set up y, my x is decided automatically by this system of equalities. So I basically control y, and I do not control x. And now I want to have uncertainty here. What will happen with it? The uncertainty will represent, as I said, either demand or generation uncertainty. And I will take the assumption first that the uncertainty is ellipsoidal. It is ellipsoidal because it allows us to deal with SDPs. So as I said, I do nonlinear optimization, conic optimization, and what I wanted to see what we can get here, a little bit practical with conic optimization. Can we get anything with conic optimization in this problem? And therefore, I needed this assumption about ellipsoidal uncertainty set. At the end, I'll show that we can also do differently without this assumption. So ellipsoidal uncertainty set, and this set will be based on the normal distribution. So we'll just say that our demand is normally distributed with a certain correlation matrix. And the way we construct this sigma, it is basically related to a correlation matrix and the chance constraint that could be analogous to our robust optimization. I won't go into detail here, but I think many of you know what I mean here. So the two-stage nature is reflected in the fact that I say the following. I need to find my control variables such that for any realization of the uncertainty, there exists the second stage variable, so my state variable, such that my AC power flow equations hold. So it solves my AC power flow equations for the given realization of the uncertainty, and my bounds hold. And we're lucky in the sense that the uncertainty here, it is incorporated in a linear way. We could still do the same stuff if it was incorporated differently, but this makes the problem a bit simpler. So if you look at this, you can immediately see that the problematic part here is this. We have an equality which must hold for every realization of the uncertainty. So what do we do with that? And both good and bad thing of this equality is that we actually cannot get rid of it, because I cannot say that y, I just remove y and I solve a problem in x and zeta, because y is my control variable. I really need to know the value of the control variable. I cannot have my control variable as some function of uncertainty. I want to remove x, in fact, because I'm absolutely not interested in the value of x. I just want that x exists. But I cannot easily remove x because I cannot express from this system x as a function of y in a closed form. So if we go a bit into detail, because I think that was the main conceptual question for us, for which we could not find an easy answer in the literature when we started solving this. So I want to use a two-stage robust optimization. Normally, what I would say, I want to find some decision rules of y and z, and I want these decision rules to be good, to give me a good objective value and feasibility for every uncertainty realization. However, in this case, I cannot say that the decision rules are just good, like some rules which I can parameterize. Because in this case, the decision rules are given and fixed. This is this decision rule. If I use any other decision rule, I will not be feasible for this system of equalities. So basically what I want to do here, I don't want to remove this equality, but I want to use it. And what I want to remove x. In fact, I want to write this decision rule somehow in the best way in a closed form, but could be some other way. And I want to write x as a function of y using this system of equalities. That's our main goal. So maybe questions here. Okay, so when we figured out that we cannot just remove y, like substitute x everywhere as a function of zeta and use the standard robust approach, because if we did that, then it would imply that we can somehow control x as a function of zeta, but we cannot control x as a function of zeta. It just flows according to this system. So we realized that we cannot do that, so we have to do something else. And we decided to do as simple as possible. So namely, I want to deal with this equality. I know that this equality implicitly defines my decision rule. And I can think about this equality as an implicit function. So my x, y of z is an implicit function, which is given by this system. What can I do with this implicit function? I can approximate it with this first order Taylor approximation. And what we did, what that physically would mean is that I just linearize this guy by taking its first order Taylor approximation. So I do this. I just now replaced all my equalities with their first order Taylor approximation. From here, I can express x. So this would be a system. I'll show it next. I can express x from here. And this x as a function of y would give me the first order Taylor approximation of my implicit decision rule. And what I will say is that, okay, the Taylor approximation, of course, will not work everywhere. It only will work on a small subset of my variables. So I will also restrict myself to a small subset of my state variables. So I will say that I am here in a small subset. And why we were thinking about it, that we want to work on the small subsets, is because of what I mentioned initially, that we work every 15 minutes, we re-optimize. So we don't have this huge uncertainty. And basically our idea is, I already have a good solution. Can I move somehow around this solution without going too far to still be robust within this 15 minutes uncertainty? So that was the idea. There is a question, Jan.
So given a y, is then the state variable uniquely determined, or are there more solutions for X possible?
Yeah, so that's a good question. Let me think. For every X, there is always a unique Y. Now the question is, can it be that for different X's give me the same Y? Right?
Mm-hmm.
It can be that different X's give me the same Y.
Okay.
Yes.
Okay.
So actually, this is like formally how we do it all. Because of what you said, it creates certain issues when you start proving convergence and everything. So what you want to do to make it sort of nice, you want to work on subsets of Y's and uncertainty, then you can do the whole proof. And when you work on these subsets, you have to constantly think about the fact that there could be two X's, but you can still show that it works.
Mm. Thanks.
Any more questions? Okay, so then we do this. And if we do this, then if I now formally rewrite it in a bit shorter way, so now this incorporates on all my linearizations, and from them I express my X. So now I have X as a function of Y and zeta, and I am very happy. So this is my first order approximation. And I included my constraints, which say that I'm within a subset, into all my nonlinear constraints. So they're now here. And now this one, I can just substitute everywhere. And then I will get this situation. So I just substituted the linear part. And my constraints also turns into something that is much simpler. So before I had this, that for any zeta there exists X. Now I just need to make sure that for any zeta, this expression holds. Then I definitely know that there exists X. So you can ask me here, because that is a valid question. Why do I only linearize this and why don't I linearize this? Because this kind of thing is still complicated. And the answer is because I wanted to use conic optimization. You don't have to do that. And that is a good question of what would be to do better. But at this point, the idea was that the less we linearize, the more maybe we keep from the original problem. We wanted to stick to the original problem as much as possible, and we hoped that this would give us more precise results. And actually, this will indeed be the case, as I'll show next.
Olga, one question.
Mm-hmm.
The D1 and D2 matrix, these are not variables here over which you optimize, right?
No. So D1 and D2 are parameters, and the only variable is Y. And zeta is the uncertainty.
Because what you're somehow doing here, it's actually a decision rule, but the one a fixed one, right?
Yeah, exactly. It is a decision. So we use a decision rule. We even know it. So like our decision rule is not. We don't even have to. Oh, sorry, I'm going in the wrong direction. Our decision rule. We don't even have to search for it. Basically, the only thing we need to do it. We just need to express it in a closed form. And we say that we cannot express it in a closed form everywhere, but on small intervals, we express it as a little, like you can think about it as we have this decision rule, and we approximate it by little pieces within small subsets. That's what we do.
Just that the normal decision rules normally are only defined on as a function of the uncertain parameter and not of Y, right? So
yes,
this would be not possible.
It is more general than this standard decision rule, I would say, even though I don't know, I don't see why in general you would not, like, I think in general you can also define a decision rule as a function of Y as well, but then it will be more complicated depending on the structure of the problem.
Yeah, I think because you plug it into the constraints normally, you don't need to depend on the first stage variable, but okay.
Yeah. So in this sense, indeed, it's a bit more general. You're right. Yes. But it is in fact, as you said, it is just a decision rule. Yeah, it's approximation of this decision rule which we're interested in this particular subset. So that was actually our problem, that we didn't want to find a good decision rule. We wanted to approximate the current decision rule. And then how do we do that? And yeah, so then we get this quadratic thing. And then if you look into it, I just want to say that for every zeta, some quadratic function is non-negative. And this is a very standard result. It becomes a very standard result. So what I get then, if I write it with my zetas, so this was my ellipsoidal uncertainty. And that means that I want that some quadratic constraint holds for all value, always at the same time when some other quadratic constraint holds. And this is nothing but the S lemma. So this is the most technical slide of the presentation, I think. And the main outcome we want to take out of it is the following, that I take my standard, so instead of two-stage robust, basically it is just a robust constraint in this case. And then I rewrite my robust constraint where both my constraint and uncertainty are given by quadratic function. I rewrite it using the S lemma. And this means that every quadratic constraint is replaced by SDP constraint. And the size of this SDP constraint is the number of uncertain parameters. So by doing that, I get the following. I remove the uncertainty. So first I removed my two-stage variables, the second-stage variables. Now I remove the uncertainty. And I'm only left from my original variables with my y's, which is my variable of interest. The objective doesn't change. The constraints on y do not change. And then I say that each inequality constraint is replaced by an SDP of the size of the number of uncertainties. I get some blue auxiliary variables. So you can see that both y's and these blue auxiliary variables, they're all incorporated linearly everywhere, except for one part, which is here. So by this whole process, which we were doing, what we did at the moment is we reduced the problem to a smaller subset. Within this subset, we took an approximation. This approximation we replaced by another problem. This is still a hard problem. It is non-convex, but while before we had a two-stage problem, which basically means we have infinitely many variables, infinitely many constraints. Now we have a problem which has finitely many variables, finitely many constraints, but it has these complicating constraints. In general, this would be hard, but because we work on these very small sets, actually I can solve this problem using alternating projection. So I project on this, then I project on these equalities, and I do this several times. And because of this small size of the set, we cannot go too far crazy, and it works well. So in this case, these constraints are not a very big problem. And therefore, we still use this approach. So to sum up, what we do, I see a question.
So can you go to this slide indeed? So so AJ and also sigma are given, and that's data.
Yes.
So I then guess that the robust counterpart, if you simultaneously diagonalize sigma and AJ.
Sigma and AJ, yes.
If you simultaneously diagonalize that, then instead of an SDP, I think you can reformulate it as a quadratic problem. And that's in fact in the paper right. I have with Ronnie.
We didn't try this. I think I know which paper you mean. We didn't try that because I've seen a paper which was trying that, and I thought, oh, that would be something, but I would not be able to say if it would perform better or not. Yeah.
Okay. Yeah. That's.
Yeah. So I'm not sure. Like, it could be a good idea. Yeah.
Yeah.
Any more questions? Okay, then let's say to summarize what we do, we look at small subsets of our second stage variables, and for each subset, we approximate our quadratic equalities with a linear function. which amounts to taking a first Taylor approximation of this decision rule. And we eliminate X as a result of that. We use S-lemma to eliminate the uncertainty, and then we solve the resulting SDP, which possibly has quadratic equalities. And I think one more thing maybe for this SDP, why it actually works well, is you need a starting point for alternating projections, right? And as a starting point, we use SDP relaxation, and it gives a very good starting point. We only need to do a couple of projections. It could be related to the problem structure. I would not bet that it is always the case, but for this ACOPF problem, it gives a very good starting point. So, and at the end, we do feasibility check for selected values of the uncertainty. So if we now look into theoretically what this can give you, actually you can't prove very much, but the only thing we could prove here is that you can decide some level of constraint violation which you want, and then you know is that if your uncertainty set is small enough and all your subset of states variables are small enough, then your equality constraints definitely hold if the resulting solution holds, and your inequality constraints cannot be violated by more than this delta which you predefined. However, what small enough is always a bit of a mystery. So we can consider many subsets, we can consider one subset, depending on how much time we have. We can, I'll see showing the experiments. And then this condition says that the uncertainty set should be small enough. And for our setup, it works just by nature of the setup, but in general, you can have larger uncertainty sets. In this case, you would need to split it. So you can show exactly the same results, but then you need to split the uncertainty set into small enough subsets. If we now throw it into a ACOPF problem and see how it works. So what we will do, we'll take the nominal solution, we will look only around it. If we can see something better, we'll find another solution, we will look around it until the moment when we cannot find anything better. And so that's basically local. We don't try to go more global. As I said, for our non-convex quadratic SDP, we solve the SDP relaxation and then do alternating projections. We use Gaussian uncertainty to check the robustness. So I say that our quadratic constraints, we are robust against the ellipsoid, but we actually try to test harder. So if we use the Gaussian uncertainty, we sample also outside the ellipsoid. And the higher the dimension, the more we sample outside the ellipsoid, actually. But since robust optimization is conservative and Gaussian uncertainty for engineers is much easier to understand than some ellipsoid, we did it like that. And also to stress test our model, actually, does it work then or not? And as test cases, we use standard mud power cases. What we get then is the following. The main column is here. We have several benchmarks. The first benchmark is nominal, so just nominal solution. We reduce the intervals there a little bit, such that the nominal solution also actually has some sort of robustness, but basically it's a nominal solution with a tiny bit narrowed intervals everywhere. We have DCOPF. So DCOPF is this linear relaxation which is used now, which I said that people are thinking about moving away from, but now they use this. So what we did, we just robustified it. That's what is frequently done in the literature. People robustify DCOPF and use this solution for ACOPF, so for the nonlinear problem. Then we use the SDP. This SDP benchmark is the benchmark which basically does the following. It eliminates it's a bit, I would say, arguable approach, but that's the only SDP approach we could find. It eliminates the control variables from the problem and then solves the two-stage problem with only second stage variable. and it defines the second stage decision rules using standard two-stage robust optimization, as if we could control the second stage rules. Well, yeah, like, well, we gave it a try, I would say it like that. Maybe also I misunderstood exactly how it was implemented, but that is what we implemented as this SDP benchmark. So this SDP benchmark, the decision rules which you get as a result, you have state variables are huge. That's also why we want to eliminate them. That's 2 multiplied by the number of buses variables. You have a lot of state variables. Moreover, you have some, the way they did it here, at some point you need an SDP relaxation of this thing. So you get a huge SDP matrix in this SDP approach. And you will see that this is not scalable, but it was an interesting benchmark to compare with, and Taylor is our approach. So what we have concluded is the following. In general, DCOPF actually works pretty well, but often it cannot find a solution. So if you see a small number here, it's good. The smaller the number, the fewer violations you have in experiments. And 0, it means that in all experiments, there was absolutely no constraint violation. If there was at least one, it already will count as violated. But the problem with DCOPF is that frequently it cannot find a solution. So here, it could not find a feasible solution for uncertainty. And I didn't say what is uncertainty. Uncertainty is calculated in percentage of loads. So the correlation matrix is constructed such that I have a normally distributed uncertainty within 1% of load, 5% of load, etc. So I allow absolutely all demands to be uncertain, which is quite heavy push on the system. This is by how much I allow it to be uncertain. And with our problem, for these very tiny cases, you see this case with 6 buses, case with 9 buses, our problem works very well for these cases, and we can even go for higher uncertainty. And that is because this case is constructed to be very flexible. So these are special cases. Yeah, so this case is constructed to be very unflexible. This case is constructed to be very flexible, and we can see it in the results. Now we can look at a bit higher cases. So for our approach, we can look at the case with 30 buses, 57, and 818 buses. When we have more buses, we also can go for less uncertainty because it accumulates. For each bus, you have 1% of uncertainty for each bus with demand. We constructed our approximation such that our each constraint we looked at basically 5% chance constraints. That's how we constructed our normal distribution. And therefore we said that, okay, if we lie here sort of within 5%, it is more than impressive, because in reality you have many, many constraints, not only one constraint. So this problem is robust against normal distribution, much wider than just against the ellipsoid. It works up to this size of cases, but as Dick asked initially, the real size of cases is like 6,000, 12,000, etc. So we are not there yet, because beyond that, we have time issues and we start getting numerical issues. You can see here the SDP approach, the other one, because of these big SDPs, it cannot go beyond 57 cases. And DCOPF also for large cases becomes less precise. That was also something which was interesting for Dan, who is an engineer. Does DCOPF work robustly, or do we need an alternative? So it seems that we need an alternative. And the one we have works nicely, but it's not so scalable. And yeah, there is a question.
Yeah, so in fact, so also in your approach, you have to you have an SDP. So is that also the bottleneck in your approach for scalability?
Actually, in our approach, it is much less of a bottleneck, because it becomes a bottleneck here, but it becomes much slower a bottleneck because it is much smaller SDP.
I see. But now it is a bottleneck for the larger sizes.
Yes.
It's due to the LMI.
Due to 2 things. First, LMI, and second, projection. projection gets less stable. So this, yeah.
Okay, yeah.
So that was indeed a very good question, because we were trying to figure out what prevents us from it. And yeah, of course it was SDP, but also the projection started working not so well. And then what we decided is like, okay, we have to give up conic stuff. We have to go linear, because yeah, then you get much more scalable. So what if we linearize everything? And indeed, we had these quadratic equalities. We have these quadratic inequalities. What I did before, I only linearized that, but I could also linearize this as well. So I would get something like this, just all these D1, D2, Cm, they're all just parameters. My variable is still y. Here, this x, I can still substitute. I can absolutely do the same what I did before. And moreover, the approaches are analogous, because you can always say that this is equal to some control variable. So you can turn this into an equality, and you can say, oh, sorry, some state variable. You can say that this is some state variable, z, which is equal to this, and then you have an inequality that z is not negative. So you basically increase the number of state variables, increase the number of equalities, but you still get a quadratic system in equalities, and you get some non-negativity here. So theoretically, the approaches are the same, but they're applied to different formulations, to different set of state variables. And when we did that, we get then the following. Again, we have a constraint here, which must hold for all zeta in the uncertainty set, but this is now a linear constraint, which is very simple. And the uncertainty set here does not have to be ellipsoidal anymore. It can be absolutely anything, as long as it is compatible with a linear constraint. If I use ellipsoidal uncertainty, I will get second order Cohen problem instead of SDP. And I will not need the projection. So basically, by doing this, I eliminate both bottlenecks. And the conversion guarantees are the same, at least in theory. And so our question was, okay, is there anything bad in this approach, or is it really much better than what we did with SDP? And the answer was that this is actually less precise. So if we look in the experiments, so the experiments were done by my students, not by me. So you see that the format is a bit different. Here you will need to look into this column. And while I reported the number of violations, he reported here the number of feasibilities. So the higher the number here, the better. That is the most important column. And you can also see that here there is a difference. We split into two types of uncertainty sampling. Before I sampled from normal distribution. He sampled from normal distribution. He saw that it doesn't work anymore. And he really had to sample from the ellipsoid. So the robust problem which we get, it stays kind of robust within the ellipsoid against which we ensure robustness. But if we want to interpret it using normal distribution, so we basically sample from a larger set, then we cannot do that anymore. You can see, for example, case 30. Case 30 was also feasible for our approach, and we got the very good feasibility results. Here, if we're within ellipsoid, we're still pretty good. So this is our robust approach. This is nominal approach. DCOPF is very frequently infeasible. That's why we don't report it. And SDP does not scale, so we also don't report it here. We only consider it, compare it with nominal. So robust still does better than nominal. If we look at the normal distribution, then we don't do better, at least in this case. If we look at other cases, we still do better than nominal, but we don't do very robust. So we don't look, we can't go that far. But if we stay within the ellipsoid, we do pretty robust. The problem is, of course, that the size of this ellipsoid basically goes to 0 when the dimension grows. So that's the question. How do you sell it to practitioners? Yeah, they probably will still want to have some distribution interpretation. but within the ellipsoid, we were still quite robust. Moreover, we could go to much higher dimensions. So the highest case we checked here was the case with 13 hundreds of buses. And it also worked pretty well. So we were not restricted here by the time or the size. We could go higher. It was just like how far I could push my students. He had a master's thesis. I could not push him too far. The main conclusion here is the following. So you see here that when we are within ellipsoid, we're still robust. There are hundreds everywhere for most cases. We do much better than the nominal model. The nominal model with increasing dimensions doesn't go well. So we cannot just hope that the nominal solution will still work, even for these very tiny uncertainty violations, because of course this tiny uncertainty in this case happens at almost every bus. So the main takeaways for us, we wanted to do something with decision rule, with this nonlinear decision rule, and it turns out that looking at piecewise linearizing this decision rule works. It could be that Taylor expansion was not the best way to piecewise linearize it, but we were happy to see that at least the idea is promising. This works for small levels of uncertainty. In all numerical experiments, if I go back, you could see these are the levels of uncertainty as a percentage of demand on each node we could deal with. And if we linearize oil constraints, we get much more scalable, but less precise. So what do we want to do next, or what can be done next here? We thought about piecewise approximations, not even in the context of uncertainty, but even maybe without uncertainty, just ACOPF equalities, because with uncertainty, without uncertainty, they are a problem. And then how do you find better approximations? Better could be faster, better could be approximations which allow you to provide better theoretical guarantees. Now with Taylor approximations, you can't say much about theoretical guarantees. So we thought about maybe doing some machine learning here, either approximating just equalities with, I don't know, neural network, which gives you a huge IP. So maybe that's not the best way to go. I have seen that Yanis did something with two-stage solutions by approximating the second stage value function. I don't know if this kind of approach, at least as idea, could be suitable here. But yeah, so something that would allow us basically to increase precision and decrease scaling while staying in the piecewise framework, let's put it this way. Also dealing with larger uncertainty sets. You could think not about this 15 minutes through optimization, but more long-term, then what would you do in this case? And then we probably would need to incorporate partition in the uncertainty set. Also, feasibility checks. I said that at the end, we do feasibility check on some uncertainties. And you can say that if you check really many uncertainties, then you sort of are within certain probabilistic guarantees. But could we do better than that? Because, again, our approach is approximation. We cannot say it's outer approximation, inner approximation, it's approximation. If there was a way to do a feasibility check, we could do a simpler and rougher approximation, but then we could have a faster and reliable feasibility check. I tried to do some polynomial optimization here. It worked, unfortunately, very badly. Yeah, there could be other ways. More efficient implementation, of course, as always, and also finally some other problems. So the water and gas problems, they have very similar structure and similar sources of uncertainty. That also would be interesting to see if these good things, they work only on ACOPF, or are they also typical for these problems, because the theory works for any nonlinear problem. It doesn't have to be ACOPF. So that was it, I think. And thanks a lot for your attention. And I will be glad to answer any questions.